Hello guys, I'm audible. So starting in few minutes. So what we are discussing this week. Okay. So what we are discussing in our last class, we have started our discussion on fluid motion, right? We have seen the linear motion. Then we have seen say it can have the rotation, it can have the shear deformation, and what we have seen. So we have noted down this last equation, the vorticity vector, right? This is what we have written, right? Hello, hello. Please check it out. Now, so the next we have to see something regarding a few things we would like to discuss. We have discussed the angular deformation rate also, right? We have discussed the angular deformation rate, right? Shear deformation, shear strain rate. These all things we have discussed, right? So few comparisons we will take from here. Okay. Hello, hello. I'm audible. Hello, I'm audible. Okay. So here, note down the special case we would like to take. Special case. Then we will move on to the mass conservations. Suppose we have a situation in our A special case. Actually, I was informed personally 8:50, so I thought the class is from 8:50. Now, let's say we have the axis x and y, and we have the fluid element like this. This is my fluid element, which I'm showing you, which is coinciding with this axis. Or let me just make it by different color. Now here, let's say I told you what is the definition of rotation. Rotation is nothing but the average. What we have written. Tell me, guys. Average rate of rotations we have written with the sign conventions. Yes or no? Average rate of rotations we have written with the sign conventions. Yes. Now, when you think of this special case which I'm discussing, the first one, here it is very, very important. Now, when the my fluid element is rotating in the same directions with the same rate of rotations, let's say the fluid element is being rotating like this. After deformation, the shape is something like this. Means this particular axis, let me call AB, it has been tilted by AB dash, and initially this is CD, then this will be tilted by C dash D dash. So here this AD as well as AB both has been tilted by the same amount uh, in the same directions like this. And in the notations of what we have discussed that this is a fluid element. When it has been rotated like this, we have discussed this is alpha, and this is beta, right? Check it out. What we have been notated. Alpha dot is from vertical, beta dot is from horizontal. Please check it out. Correct, right? Is that correct? Alpha dot from, yes. So here I'm calling this V, let's say alpha dot. Here this is beta dot. Both are rotating in the same sense. So what is my omega x phi? or omega about z axis, because it is in the xy plane, so rotation will be there about the z axis, which are perpendicular to the plane of this laptop board. Now here, what is my average rate of rotation? Alpha dot. uh, Clockwise I have taken what? Tell me guys, what about the clockwise rotations? That is negative. Anti-clockwise rotations I have taken positive, right? Getting my point? So here what I will be getting, my different? Tell me guys. So here alpha dot plus beta dot, both will be positive, and both are equal. Both are equal, right? So both are equal and they are rotating in the same sense. So what we can write? Alpha dot is minus, alpha dot is what? Minus of beta dot, right? So what we can write? Omega xy. Omega xy can be written as half of 2 alpha dot, that is equal to alpha dot or beta dot. Is that clear? Pure. This is called pure rotation case. What is the meaning of pure rotation? What is the meaning of pure rotation, guys? When the fluid edge tilts in the same direction and equally, that is my fluid. That is called as what? Pure rotation case. Please make a note of it. Correct. This is my pure rotation. Note down. When the fluid element edges tilts in the same direction and by the equal amount and by the equal amount, we call this to be a pure rotation case. Any shape changes are happening, please check it out. Any shape changes are happening over here? So what about shear deformation? What about shear deformation rate? 0. Now why I have written this alpha dot is equal to minus of beta dot? On what basis I have written? Anyone can tell me? See my difference. It's a very simple and very fundamental thing. I told you when the shear deformation can happen in xy dot, when we write alpha dot plus beta dot, right? We know this. This is the formula we have, the shear deformation rate. And for shear deformation rate, initial angle between the two perpendicular lines minus final angle dot, right? This is the definition of shear strain rate or angular deformation rate. But my different here, when you observe, initial angle is what? Between the two perpendicular line AB and AD is 90 degree. And even after deformation also, let's say deformation has happened, still the angle is what? 90 degree between the two perpendicular lines, which were initially perpendicular. So that is what I have taken the reference AB and AD dash, right? It's still 90 degrees. So 90 minus 90, that is being 0. So this is equal to 0. That's why alpha dot is equal to minus beta dot. Is that clear, all of you? So this is called a pure rotation case. This is nothing but we call this to be a pure rotation case. Any example we have pure rotation case? Just like a solid body rotation, right? In a tank, you have the fluid. In a tank, you have the fluid, and this fluid has been rotated by some, for example, by some external source. We have rotated this fluid, right? So when we rotate this fluid, even though it has the viscosity, even though this region is a viscous flow region, but still this fluid element which is there in the container will not be able to take the different shape, right? The shape will be what? Whatever the initial shape is there, that will be the shape after some time also. So this is called force vortex flow. This force vortex flow is a pure rotation example. Now here in the force vortex flow, there cannot be any force. There cannot be any force because of the viscosity, right? Because there cannot be any torque. Torque by viscosity, when you write, what is the shear force into radius, right? Fluid element cannot be rotated. Fluid element cannot be rotated. For example, from center of mass to some radius is there. This is my fluid element. This fluid element cannot be able to rotate. Why it cannot be able to rotate? Because of the viscosity. With the help of viscous force, it cannot rotate because this viscous force is zero over here. Why this viscous force is zero? We know that mu into dou u by dou y into area, right? So here, my different, what is happening? Dou u by dou y is exist, right? Or what we can write? Shear stress we can write directly. What is the shear stress? Shear stress, what we can write, guys? Mu into gamma xy dot. When this is zero, this will also be zero, and tau is nothing but what? Tau xy is nothing but whatever the shear force is there divided by what? Area over which it is acting, right? If this is zero, this will also be zero, right? So we have to write shear force cannot produce any torque in the force vortex flow, right? Whenever we take any fluid element in a container and when we try to rotate it, right, it will only rotate because of the external agency. This is the external source. This is the external source. Or where you can observe this vortex flow once again, or rotational flow, where you can observe any other situation where we can observe this thing in a centrifugal pump, right? In a centrifugal pump also, right? In the impeller, the blades, there also you can observe the force vortex flow. Getting my point? Yes, in a mixture also. Now all of you please make a note of it. Once it is done, let me know. Now here we have one more case, pure shear case. Let me discuss that. Pure shear case. Alpha is equal to minus beta dot. I have explained, right? Because shear deformation is getting zero. This is getting zero. Why? There is a no initial angle and the final angle is being same 90 degree. Shear force is zero, right? I told you because shear stress is zero. What is the shear stress? According to Newton's law of viscosity, mu times of shear strain rate, right? Mu times of, see, in the solid mechanics we used to write g times of y, but here we used to write mu times of y dot, right? Y dot is what? Dou u by dou y plus dou v by dou x, right? So in case of what we call in case of this one, is completely getting zero. If it is getting zero, shear strain rate itself is getting zero. The shear stress will also be zero. Shear force will also be zero, right? And if shear force is zero, torque will be zero because this is zero. Then viscous torque will be zero. Now, you will come to know this equation, right? Because right now, what you have observed this equation, dou u by dou y plus dou v by dou x. Stokes law of viscosity. This is the Stokes equation. This is the Stokes equation, right? This is the Stokes equation. In our first chapter in fluid property, there was no perpendicular flow. That was earlier zero. So that is how you got the equation, this equation. So there we call this term to be what? Whatever the gamma x y dot is there we call dou u by dou y directly without telling dou v by dou x. Is that clear, all of you? Now let me remove this. So we will discuss this Stokes equation, no need to worry, in the laminar flow. As of now, when we derive the Navier-Stokes equation, there we will use it. Yes, for a static fluid, it will be zero. But that depends on for the static fluid whether it has been driven by the plate or not. If you are not at all giving any velocity to the plate, just what we have discussed, simple cuvette flow, then straight away that is zero. No viscous force, no drag force will be there on a fluid element. In a static fluid, there cannot be any shear force. Remember that. Now, is it done, all of you? All of you have noted down? Now, understand the special case B. I think A case we have discussed. Note down the pure shear case. Now, here you have to be little bit patience regarding this case, as it is slightly required the mathematics. This is x and y, for example, and we have the situation, this fluid element. Earlier we call A, B, C, D. Now this A, B, C, D, let me just take, it is taking a shape of like this. It has been deformed, and now it is taking a shape of like this. This is alpha dot, this is beta dot. Here what is happening, alpha dot, that is equal to beta dot. Don't write minus beta dot, plus beta dot. Here both are rotating equally, but in the opposite sense. Both are rotating equally, but in opposite sense. Then tell me what is the omega xy? By the definition, we know that it's average of that. But beta dot will be positive and alpha dot will be negative according to our sign conventions, because alpha dot is clockwise. And clockwise we have taken negative, anti-clockwise we have taken positive. So this is minus alpha dot plus beta dot. And by putting this one, what you are understanding? When both are equal, then this will be zero. There will not be any rotation in case of a pure shear case, right? So what you are understanding, there is a no rotation. No rotation, right? But there is a some kind of pure shear deformation, or some shear deformations are happening, right? So note down what is the meaning of pure shear. When edges of the fluid element, when edges of the fluid element tilts in the same direction, in the opposite direction, in the opposite directions, but equally. That is called pure shear case, pure shear deformation. Now, one question will arise by this case. What the question will arise? What the question will arise? Let's say uh, we have the inviscid flow where the viscous force is zero. Now tell me, guys, in this particular case, what you have been observing over here. Is that possible? That can we call this pure shear case to be irrotational flow? Irrotational flow means where omega is zero, there is a no vorticity, because vorticity is what, 2 times of omega. If this is zero, this will also be zero. So all the conditions are pertaining towards irrotational case. But for a irrotational case, there has to be one more condition should be there. Like inviscid flow, here what you are observing, whether this is a viscid flow or inviscid flow, tell me. At least some deformations are happening. Some deformations are happening. So you might be tempted to think that, sir, this is giving me some results of shear force, because shear force we can write something like mu times of alpha dot plus beta dot times of area, right? And sir, here alpha dot and beta dot both are exist. So definitely we have the shear force. So this is a viscid flow. But sir, viscid flow we are telling, and here we are telling irrotational. Is that possible? Both the combinations. What I'm telling you, if any flow field is there, if flow is happening, can any viscous flow, viscid flow or viscous flow, and irrotational flow, both can exist simultaneously? That is what my question. The question is, can viscous flow, can viscous plus irrotational flow exist? Till now in gate examination, they have not tested this part. They have tested other statement. I will be telling you in short in few minutes of time. But as of now, whether viscous flow, you know that shear force is there, definitely that is a viscous force, or that is a viscous flow, right? Now, and here by this definition, by all this statement, one thing is also sure that it is a irrotational flow. Irrotational flow. Now the question mark will arise whether viscous and irrotational flow will exist together. So the answer will be no. Why it is? Why the answer is no? Anyone know that? The reason behind that? First of all, let me know whether it is over or not. Or you can also note down question number two. This is my first question, and second question would be whether irrotational flow always be inviscid flow. So what could be the answer for this question? Because when you are saying that first question is not correct, sir, that means this statement has to be true. There must be some inviscid flow plus irrotational flow must exist together. Now the question mark will arise, sir, what we are discussing right now. Because mathematically it is possible. Mathematically, when you see when alpha dot and beta dot both exist and both are equal, then we have the case where the scenario that irrotational and viscid flow is possible, right? But here, what is happening when you observe shear force, right? Mu times of alpha dot plus beta dot into area, right? And all the condition which is pertaining to this alpha dot and beta dot, when it is there, then we know that omega xy is zero. And this is only the condition for flow to be called irrotational flow. When the fluid element will not be able to rotate about its own center of mass, simply we say irrotational flow, right? Or we say free vortex flow, not force vortex flow. Now, when this condition will be there, then one condition arises, irrotational and viscous, because shear force is not equal to zero. But one more case is there, a very special case, when alpha dot beta dot both will be zero, that is equal to zero, then viscous force or shear force is zero, and then omega xy is also be zero, right? So mathematically is telling that alpha dot and beta dot when both zero, then only we can say that the irrotational flow will be equal to viscous flow, right? And the answer for this question is yes. Irrotational flow will always be inviscid flow, 100% true. Why? You have to disregard, you have to just neglect this particular case. This case practically not possible. Practically, mathematically it is possible, but practically not possible. Even mathematically also not possible. When you see the, we will discuss mathematically. Let's say maths. Now, from the maths point of view, we know that any irrotational flow field is there. Any irrotational flow field, any irrotational, any irrotational flow field has to be conservative flow field. Has to be conservative. Has to be conservative flow field. What is the meaning of conservative? What is the meaning of conservative flow field? Conservative flow field means whatever the force has been applied, they must be balanced together, right? Whatever the total flow system is there, there cannot be any viscous forces. There cannot be any friction forces in a flow field, right? Then only we can conserve the flow field, conservation flow field, right? So here we will write, suppose FDR is there, we can write phi of B minus phi of A when delta cross F is equal to 0. Let's say F is any vector. Let's say F is any vector field. I'm not talking about it is only the velocity field. Let's suppose here we are talking about the force vortex field. Force vortex field. And delta cross F is 0 means what? Curl of any vector is 0. When curl of any vector is 0, we know that that is like a irrotational case, right? Whenever we can write delta cross F is equal to 0, then we can write F, that vector we can write gradient of phi, where phi is a scalar quantity. Phi is a scalar quantity. So in this way, we can write, when we integrate, we can write like this, right? So irrotational flow field means that is a conservative flow field. Conservative means there cannot be any friction force. No viscous force should be there. If viscous force will be there, then what will happen? That will make the flow field non-conservative. Conservative means what? See, what you have done in the engineering mechanics, the net force into distance, that is equal to what? Change in kinetic energy, right? Kinetic energy, that is final, minus kinetic energy, that is initial. That is what you have written. Work energy theorem. Work energy theorem, when you see that, what you have written? Total amount of work done, right? The total amount of work done is there. That is equal to change in kinetic energy of the system. Total amount of work done by all the forces, right? So when you write the viscous force, you cannot conserve anything. Conservation of mechanical energy, conservation of any energy will not be possible, right? Conservation of energy means I'm talking about kinetic energy plus whatever the potential energy is there, that has to be constant. That cannot be constant when there is a viscous force, or the viscous energy will also be present. Getting my point, all of you? Yes or no? Conservative flow field, it is very very important. Conservative field means there cannot be any friction. If the friction is there, that will make non-conservative, because that will take some of the energy. Because what is the function of the friction? It takes some of the energy of the body. That's why the body will come to the rest condition after some point of time. Just like just like what happens. Yeah, that is what I'm saying, that in case of vehicle, whatever the wheel is there, in case of wheel, if you want to apply the brake, how the brake systems is working, the friction will be generated, and after some point of time, that pure rolling motion will be stabilized. That stabilized of pure rolling motion will stop the what wheel or vehicle. So for maintaining the pure rolling motion, friction has to be there, right? Friction has to be there. Now, once the pure rolling will start, that will not play any important role, right? So that frictional losses, yes, that should not be there. So mathematically, when you think in this way, and practically also, for any irrotational flow field, if you read the mathematics vector calculus, H.K. Das or any other good book of mathematics, there it is clearly written that any irrotational flow field is a conservative flow field, right? It is always conserved. There will not be any friction, right? So this has to be neglected. This kit until unless alpha dot beta dot both equal to 0, right? Make a note of it. So irrotational flow will always be inviscid flow. That is correct. Now, but the third question will be whether inviscid flow will always be irrotational flow. Whether inviscid flow that viscous force is 0 will always be irrotational flow. No, because I just know we have discussed one case. What is that? Here viscous force, even though viscous force is 0, that is the inviscid flow, right? Here we have pure rotation, inviscid flow is there, inviscid flow. But inviscid flow, if it is a pure rotation, that inviscid flow will become rotational flow. But if external torque is not there, if external source is not there, if it is 0, then inviscid flow will always be a rotational flow. But one condition, external source or external torque should not be there, right? So what we can write here, we will make one statement, general statement. Make a note of this. Inviscid flow, inviscid flow, it can be inviscid flow means shear force will be 0 and internal torque will be 0 or viscous torque will be 0. So inviscid flow, it can be irrotational flow, vorticity 0, omega 0. It can be a rotational flow. Example, force vortex flow. So make a note of it. If at all any flow field, if it is a irrotational, then definitely it has to be inviscid. Remember that. Linear deformation and pure rotation. Uh, no, see, for a pure deformation, no, that's not possible. In that case, u will be the function of both x and y. That depends on the condition, function of u and v, right? That may be possible, but a very special case that may be. Remember, you can have both. What I want to say, you can have all three things are possible for a fluid element. Fluid element can translate and can deform, can rotate also. All the things are possible for a fluid element. See here, when you observe this fluid element A, B, C, D, it has been translated A dash B dash from here to here. They have been translated in X direction, in the Y direction both, right? That is a linear deformation rate, and they have been tilted also, not with the equal amount. So both will be there. That is a shear deformation as well as linear deformation. So here linear deformation is there. Translation, sorry, translation is for all the four things are possible, right? When u is constant, right, what we say, and v is also constant, then what we say, element is there AB, it will simply translate. When there is a no deformations, there is a no linear deformation. But when the u is a function of x, then we say it will linearly deform. right? So what we are observing here, whenever u is a function of both x and y, when u is a function of x and y, v is also a function of x and y, then you will observe linear deformation, translation, plus angular deformation, plus rotation. It's a very general case, all the things are possible. Now make a note of it. Once it is done, let me know. That is what I'm saying. That depends on the function. That that may be the rarest of the cases, but mathematically may be possible. You have such a very special function where uh, for a pure rotation they will be equally tilted, right? But I don't think so that is possible, because any function I cannot able to think right now. Maybe you have to apply permutation and combination by taking uh, this thing. No deformation, that is correct, but he asked about the linear deformations. In the first case, v is a function of x, u is a function of y. No, linear deformation. What is the linear deformation? Dou u by dou x. U has to be the function of x. To have the linear deformation, you have to be the function of x. Otherwise, if you are saying that it is a function of y, and you are saying that function of x, then this will be zero. And y direction dou v by dou y, this will also be zero. And anyhow, perpendicular it will be zero. Linear is strain rate. Getting my point, right? So so all you can permutation and combination you can try by having the functions. Now, can we move to the next one? So we have discussed the problem or not? Mathematically, so many things are possible, but practically, chances are very, very less. Already, these are the things which has been tested, right, in a wind tunnel testing machine. So mathematics will give you broad sense of understanding that how many permutation and combinations are possible for a particular research field. That doesn't mean that for every mathematical solution you will run behind. You will be taking that solution to the experimental and do the experiment. That will be the time wasting. Now try to solve this question very quickly. So I have discussed the very broad things when you discuss aerodynamic subject. Very easily you can grab it all the points when sir will discuss about the other potential flow and all. What is the meaning of potential flow? Irrotational plus incompressible flow. Getting my point? Potential flow means irrotational, incompressible flow. There, directly sir will discuss. He will not discuss what is the meaning of complete detailing of irrotational, complete meaning of incompressible. That is our duty to discuss over here completely, right? Now, so they have given the velocity field u as 2xy, v has been given as x square z, and they are asking what is the velocity vector at 1111, right? Correct. Yeah, correct. So here, when you write the vorticity about x, Then what we can write? What is it about yz? Then what we can write? Dou omega by dou y minus dou v by dou z. What is t about y-axis? What is t about xz? This we can write dou u by dou z, dou omega by dou x minus dou u by dou y. So what you're understanding, these are the, see, what is the meaning of this? Or what is it about x axis? When you're taking the what is t or rotation about x axis, that means you are in the yz plane. That is the meaning of that, right? Do not confuse. So now tell me guys, what we can write? Dou omega, omega is 0, so dou omega by dou y will also be 0. Dou v by dou z will be minus of x square, and that to 111 position, that will be minus 1. This is minus 1. Sorry, that will be plus 1. What about omega, about the y-axis? Dou u by dou z, that is 0. That is 0. So total 0. Because this is 0, this is 0. Dou v by dou x, that is minus 2xz. Dou u by dou y, minus 2x. So what you can write? Minus 4. So finally, what is the vorticity vector? Omega x I cap, omega y j cap plus omega y k cap. So what we can write further? I plus 0 j cap minus 4 k cap. So D will be correct, right? So please guys revise after my classes. Otherwise you will be not be able to follow. Done? All of you have noted down? Can I move to the next? Yes. Note on the next concept, conservation of mass. So for anything deriving this conservation of mass, here we can make use of RTT equation, but I'm not going in that way as of now. At the starting phase, we cannot discuss the RTT right now. That is the Reynolds transpose theorem. So what I'm telling you, I will be telling you in a very simple word. Conservation of mass is a very important thing. That will give you the validity of what? The validity about the fluid mechanics. Fluid flow field. Whether fluid flow exists or not, any function in a flow field, whether it is there or not, sigma or maybe psi or maybe sigma psi or phi, any function is there in a flow field, in a fluid flow field. If it is there, it has to satisfy this conservation of mass. It has to satisfy. Right now, you want to check it out. Let me tell you one equation, or let me discuss that. This is the validity of the fluid mechanics. Now, what it tells you, suppose we have the control volume. If you are following Eulerian approach, based on Eulerian, what is it? What is it? Tell me, guys. Eulerian has said that you have to consider one control volume, or it is better that I will discuss in the next page. See, what I'm discussing, let me consider one case of control volume. Let's take this is a control volume, right? Let's take this is my control volume, which I'm drawing. Perfect. Because we are not following single fluid particles, we are focusing our attention on a control volume, on a control this control volume. On this control volume, my dear friend, let's take, for example, no, previous slide, no need to write. This thing, no need to write. I'll be telling you once again. Same thing I'm writing over here in this slide after discussion of this control volume, right? How these terms are coming, that is important. For example, suppose 100 rupees I have deposited, and this is my bank, right? And let's take one day. For a first day you have deposited 100 rupees. On the very next day you are taking the, or maybe after some point of time you are taking 50 rupees. So frankly speaking, in your bank account, what should be the amount has to be left in your particular bank account? For example, you have the bank account, what should be the amount when you take? So you will find 50 rupees plus some extra amount will be there. That extra amount is nothing but interest. That is the interest that will be there, maybe 2 rupees or 3 rupees, that will be added to the 50 rupees. So what actually you're doing, 100 rupees is there, that is equal to how much of interest is there, that is a time, for how much time you are keeping that money, and that is equal to rupees 50. That is what you have withdrawn. So what you are writing, mass flow rate, consider now money as equal to mass flow rate that is being going in, that is equal to dou m divided by dou t in that control volume, plus how much of mass flow rate of money coming out, right? So this is what we are writing based on the uh, Eulerian approach. Make a note of it. So what is the statement? Total mass entering into the control volume, right? That is equal to, or we can write, yeah, that is equal to net change of mass, within the control volume, within the bank, during delta t time period, plus total mass leaving the control volume during delta t. Sorry, yeah, during delta t. Here also you can write during delta t. So what you are observing, guys, same thing they have written, right? Because see, one day you have taken, on a first day 100 rupees you have deposited. On a very second day, on a very next day you have withdrawn 50 rupees in your bank account. There will not be any, hardly any changes will be there in your money with respect to time. So 100 rupees will be there, and you have withdrawn 50 rupees. 50 rupees will be there, right? So that is what the situations. Let's say, for example, 100 rupees is there, and you are withdrawing 100 rupees completely. So any storage will be there? Nothing, right? No storage, no interest will be there, right? So for a steady flow, what we can say? For a steady flow system, what we can say? There will not be any storage. So whatever the mass flow rate in will be there, that is equal to mass flow rate out. Yes or no, guys? 100 rupees coming, 100 rupees out. Nothing is there to be getting what? Nothing amount has been left out in your bank account, so that we are getting interest on that left account, left amount. Is that clear, all of you? All of you getting my point? Is that clear? Tell me, guys. This particular statement only they have written like this: total mass entering into the control volume minus total mass leaving. That 100 minus 50. That is what 50 is happening. 50 rupees plus extra whatever the charges is there. That is the net change of mass within the control volume. Is that clear, all of you? Tell me, guys. All of you getting my point? Yes. Whatever the money has been there in your bank account, that is what which is being changing with respect to time. That means money which is being left out plus some interest together it will give the value this particular term. So don't think that it is giving you only the interest. It is giving you interest plus amount which is being left out after withdrawing certain amount. Now, otherwise you will not be able to understand why this extra term is coming. You will think, sir, this has to be there. Then why this extra term is there? That is what the net change of mass within the control volume during delta t time. Now, all of you have noted down. Can I move to the next? Is it done? Now, guys, try understanding. If I follow basically to have a better understanding, let me discuss this thing by Lagrangian approach. Lagrangian approach. In this approach, we will try to understand this particular fundamental concept of this validity or of fluid mechanics, or we will say conservation of mass. Further, we will say it is a continuity equation. Now, here I am focusing on a fixed mass or a control mass. Rather than focusing on a control volume, I am focusing on a control mass. This control mass, my dear friend, I am focusing. So, what is the mass of this ball? Volume into density. Take the log on both the sides. Something you will be getting. Now, differentiate with respect to time. Differentiate with respect to time. So, 1 upon m dm by dt, 1 upon v dv by dt, 1 upon rho d rho by dt. Right? So this is what we are getting, my different. Total change of mass of any body, any ball, your mass, whatever the mass is there, that cannot change, right? That cannot change with respect to time. That has to be zero, right? So what we can write, 1 upon v dv by dt plus 1 upon rho d rho by dt has to be zero. Has to be zero. Now what is the d rho by dt we can write? What is the d rho? Let's say density is a function of x, y, z, and t. For example, for a very general example, I am saying, let's say the density is a function of x, y, z, and t. Then by the rule of total differentiation, what is the d rho we can write? Dou rho by dou x into dx, dou rho by dy into dy, dou rho by dz into dz, dou rho by dou t into dt. This thing we can write. This thing we can write. Now, if I divide by dt, 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 so what we can write, this dx by dt, u, this is v omega. So here what we can write, u into dou rho by dou x, v into dou rho by dou y. See, those who don't like to see the derivation directly, you can close your eyes and whatever the final equation will be there, that you can take it. But I cannot proceed without telling this small derivation which helps you in understanding how we are arriving to the final equations, right? It's up to you whether you want to note it down or not, but definitely it is worth to see these derivations. Now, because sometimes to understand the steps of derivation will it requires effort. So if you don't want to put that effort, if you want to save it, you can have the what you can completely ignore that, and finally you can come to the equations. But I cannot directly write the equations. That will not happen in my class, even though I take extra class, but I won't do that directly writing the equations. Now here, this is what d rho by dt is there, and this is what the equation. What about this term? Volumetric strain rate, 1 upon v dv by dt, that is a summation of linear strain rates, that is dou u by dou x plus dou v by dou y plus dou omega by dou z. That is the volumetric strain rate. Now make a note of it. Once it is done, let me know. Is it done? Can I move to the next? Now you try understanding what we have written. We have written nothing. Here, if I just substitute over here, what I will write in the final equation, the final equation will become like this: dou u by dou x, dou v by dou y, dou omega by dou z, plus 1 upon rho, that completely, because 1 upon rho is also there here. If I write this d rho by dt from here, 1 upon rho already there. So 1 upon rho in whole bracket, the big bracket will be there, and that is my u into dou rho by dou x plus v into dou rho by dou y plus omega into dou rho by dou z plus dou rho by dou t, that is equal to 0. So that's how you arrive to the 3D general continuity equations. But before writing, this is also one 3D general continuity equation, 3-dimensional general continuity or mass conservation equation. But before that, I would like to take some steps to solve further. So here, what you can write, understand this dou rho by dou t term I'm writing separately. Further, this term, which term? Here we can write, see, dou by dou x of rho u. What you can write? You can write rho into dou u by dou x plus u into dou rho by dou x. So this term and this term, where it is. So if I just divide by 1 upon rho, so what I will be writing? Should I multiply with that? Yes, that will be better. If you just multiply this equation with the row, 0 into rho, so that will be 0. So here what we can have, this will cancel out. So rho, what we can have here further we have, if I don't write like this, yes. So here what we can write, dou by dou x of rho u, that is rho into dou u by dou x plus u into dou rho by dou x. This term and this term, we can write dou by dou x of rho u. Similarly, dou by dou y of rho v, dou by dou z of rho omega, that is equal to 0, right? Because when you write dou by dou y of rho v, that is equal to rho into dou v by dou y plus v into dou rho by dou y, and further we can write dou by dou z of rho omega, that is equal to dou omega by dou z plus omega into dou rho by dou z. Please make a note of it. That is also 3D continuity equations. When you write in the vector calculus format, so here you can write, yeah, del dot rho v plus dou rho by dou t, that is equal to 0. Del is operator is what? Del operator I into dou by dou x, j by dou or dou y, k of dou by dou z. And vector v is nothing but u I cap plus v j cap plus omega k cap. When you multiply, you will be getting that. You will be getting ultimately this equation. This is the first equation we can write, or we can also write, my dear friend, if I modify this equation, this is generally we call conservative form of equations, right? Conservative form of equation when the density is inside the delta operator. When density is inside the delta operator. When density is outside the delta operator, we call non-conservative form of equations. What we call non-conservative form of equations. Directly we are arriving to this equation. Directly we are arriving to this equation. That is a conservative form of equation, and that is a conservation of mass. That is a validity of the fluid mechanics. Very good equations. That is a very good equations. But if I take whatever the equation we call non-conservative, that is also continuity equation. That is also tells the validity of the fluid mechanics. But that is a simplified version of this big equation, what we call 3D general continuity equation. How we can simplify further? Whatever the earlier you have written, this one. On the basis of that, we can write what we can write: rho delta dot v, because delta dot v when you do, you will be getting this term, plus what we can write, plus what we can write, v dot delta, v dot delta, v dot delta, what you can write, v dot delta into rho plus dou rho by dou t, that is equal to 0, right? So this is also you have something like this. Now we can write, yes, very good. How we can write this these two terms together? These two terms together, what we can write? Total material derivative of the d rho, something like this. Rho del dot v plus d rho by dt, that is equal to 0. Make a note of it. This is nothing but rho is coming outside the derivative term. That is a non-conservative form of equations. Equation number 2. Both are same equation. Both are same equation. No need to worry about that. These two terms together will be right, d rho by dt, because from where these terms are coming, my different, from where this whole term is coming, when you see that, from here only. Getting my point? So make a note of it. So you please try to remember this, in this format also, this equation. That is a very, very important. Once it is done, let me know. Little bit of math, you try to revise vector calculus, you will get to know everything. There's no big deal in that. non-conservative, right? But no need to think about non-conservative and conservative equations. Now, now you try to understand. Is it done, all of you? All of you have noted down? Is it done for all? Done? Done, right? Case number one, study flow. When we have the study flow, now tell me what will happen with the study flow. Which term will be gone? Dou rho by dou t, that will be gone. Dou rho by dou t will be there. Then what we can write from the first equation? From the first equation, what we can write? Rho into v, that is equal to 0. Getting my point, all of you? No, 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 no. For a steady flow, we can write dou rho by dou t. That steady term will be gone, right? So del rho v, that will also be 0, right? Or we can write from the second equation. What we can write from the second equations? Rho del dot v, del dot v. What we can write? Rho del dot v plus rho, what we have written? V dot delta, v dot delta into rho. That is equal to 0. Can we write like this? Take it out. No problem at all, right? So, yeah, make a note of it. Case number two, incompressible flow. Incompressible flow doesn't mean that density is constant. It means that total change of density with respect to time has to be 0, or d rho by dt has to be 0. So from that equation, what we can write? 1 upon rho d rho by dt plus 1 upon v dv by dt has to be 0. That means if this is 0, this will also be 0. That means volumetric strain rate has to be 0. Volumetric strain rate means what? Del dot v has to be 0. That means what? Dou u by dou x plus dou v by dou y plus dou omega by dou z. Dou omega by dou z has to be 0. That is for an incompressible flow. That is a sufficient condition for flow to be called flow to be called incompressible flow, right? That is what we call 3D incompressible continuity equation. Continuity equations. So make a note of it. Very, very important. Incompressible fluid means incompressible fluid density has to be constant. Density cannot be the function of either x, y, z, and t. If the flow is incompressible, yes, it's difficult to predict that whether the flow is steady and unsteady, because incompressible flow can be both steady as well as unsteady flow. Getting my point? Incompressible flow can be both steady and unsteady flow. Can you please check it out from the equations? So steady flow will never ensure whether density is constant or not. It will never ensure because density can be the function of x, y, z. If it is not the function of t, it can be the function of x, y, z. So steady flow will never guarantee you about the incompressible flow. Steady flow can be both compressible as well as incompressible flow, right? Now, once it is done, let me know. Now tell me this equation, the equation number 3 which you are getting, whether it is valid for which case? Whether it is valid for which case? Or we can discuss this particular question. Let me take the, all of you have noted down this thing? All of you have done with this? All of you have taken the notes for two cases, steady flow and incompressible flow? Tell me guys, is it done for all of you? Now let me discuss one question so that things will clarify. Here, under what condition del this del rho v is 0? So what is the full equation, full-fledged equation, equation number 1? What we have, when we write the full-fledged equation, delta rho v plus dou rho by dou t, that is equal to 0. This is what the equation we have. This is what the equation we have. But with this equation, what you are understanding, that if it is a steady incompressible flow, still this equation is valid, because for a steady flow, for a steady incompressible flow, dou rho by dou t will be 0. This term will be gone, so automatically this term will be 0. That is the first. What about Q statement? It is valid for unsteady and incompressible flow. Check it out. Whether it is valid for unsteady and incompressible flow. Here in this particular question, they want to say incompressible flow of incompressible fluid. You have to assume, I will discuss one scenario where incompressible flow can be both compressible fluid, it can be incompressible fluid. But for the question what they have mentioned in GATE exam, they are intentionally want from us that you need to think incompressible flow of incompressible fluid. In that case, density will be constant. If density will be constant, my dear friend, then what about the equations we have? What about the second equation we have? Can you please tell me? What about the second equation we have? When we write the second equation, dou rho by dou t plus rho into delta dot v equal to 0. Or we can also write the first equation in which way? Tell me guys. In which particular way we can write this equation? See, what is my final equation we have? Rho into dou u by dou x plus dou u by dou y plus dou omega by dou z plus u into dou rho by dou x. What the equation we have? Dou rho by dou x plus v into dou rho by dou y plus omega into dou rho by dou z plus dou rho by dou t equal to 0. When density is taken as constant, that means it is not the function of x, y, z or t. all the terms will be 0, all the terms will be 0, all the terms will be 0, then what we are arriving to the conclusions? Del dot V has to be 0. Or further, this can also be written as what? Del dot rho V, that is also 0. Check it out. If all these terms are 0, can we write these two equations to be same? Please check it out. Understanding or not? When density, I would say, that is constant, this whole term will be gone. This whole d rho by dt term will be gone. This term will be gone. Still it is there or not? Equal to 0. Check it out. It does not ensure that it is not required the condition of steadiness. Check it out. Still have confusion? Let me clear that. See, what is the equation for steady incompressible flow? Of incompressible fluid. Now, why I'm writing this big statement? This is important. Incompressible flow of incompressible fluid. For example, now tell me the equation of this. What is the equation? Study. Study. What is the from equation number 1? From equation number 1. Tell me the from equation number 1. Delta rho into V, that is equal to plus dou rho by dou t, that is equal to 0. Study means equal to 0. This term will be gone. Incompressible fluid means density is constant, right? So finally, what we can write this equation? Delta dot V equal to 0, because we can take rho from outside. We can take it outside from the derivative, as it is not the it is just like a constant. See, d by dx of something, if you want to do 2 into x, so 2 into what? D by dx of x, you can write. Same thing we are writing here, right? Now, second statement, there is the first one. What is the equation for unsteady incompressible flow of incompressible fluid? Incompressible fluid. Not tell me the equation of this one. You only tell me the equation of this one. From the starting, if I just take, what we can write? Del rho into V plus dou rho by dou t. Any doubt in this equation? Equation number 1. Any doubt till now? Tell me, guys. In this equation number 1, can we write this equation? Just check it out. Whether equation number 1 is correct or not, please check it out. This equation, is it correct or incorrect? Hello, hello, hello. Tell me, guys, whether it is correct or incorrect. Correct. Incompressible fluid means density is 1000, suppose for example, kilogram per meter cube. Density is constant. बाद में आ रहा, बाद में. Density is nothing but constant. Density is constant means what? Density is constant. What is the meaning of density is constant? Density is constant means what? Density is neither the function of x, y, z, or t, or any other variable. Dou rho by dou t automatically has to be 0. No need to enforce the condition of steady or unsteadiness. So still you have the final equation to be same. Rho, if you take outside, still that is 0. Both are same or not? So now you tell me this particular dou delta rho into V equal to 0 is steady incompressible, unsteady incompressible, for both it is valid. Getting my point or not? Tell me, guys. Automatically that term will be gone. Whatever the function of time dou rho by dou t, automatically that will be gone because density will be constant. Now further tell me, what about R statement? Is steady compressible flow. Compressible flow. Now compressible flow means what? Density will not be the function of density, can be the function of x, y, z. So here what we can write? Here what we can write? Further we want to write del dot rho into V plus dou rho by dou t equal to 0. But it is a steady, that is equal to 0. So once again we are having equation is valid. Unsteady in compressible flow, impossible. Impossible, because compressible flow, it can be the function of density, can be the function of x, y, z, and t. Compressible flow means what? Where we can say density is what? Volumetric strain rate is not equal to zero. Volumetric strain rate is not equal to zero, right? That is an incompressible flow. Sorry, that is a compressible flow. Right, that is a compressible flow. So we cannot write comfortably this equation. So this is incorrect. So PQR will be correct. A option is correct. Any doubt? Let me know this question. Whether this slide is completely you have understood or not. Very important slide. Incompressible flow, mathematically, it can be both compressible fluid, where density is not constant, incompressible fluid, where density is equal to constant. So you might be thinking, sir, in examination, in gate examination, how we come to know whether they are talking about incompressible flow of incompressible flow, incompressible fluid, right? We have to assume, because it is being proven that almost for the 99.9999 chances that if it is an incompressible flow, it has to be incompressible fluid. Only 1% or very rare case where incompressible flow will be compressible fluid. I will prove that. If it is an incompressible fluid, it has to be incompressible flow. One more statement. If it is incompressible fluid, if it is an incompressible fluid, it has to be incompressible flow. So in the examination, they have to mention incompressible fluid rather than mentioning incompressible flow. But we cannot correct IIT professor as they will take as an ego, So what we can do, simply accept that their meaning is that incompressible flow of an incompressible fluid. Till now, what you understood, you might be thinking, sir, only two things are there in our aerodynamics of fluid mechanics: incompressible fluid, compressible fluid. But there are four things: incompressible flow, incompressible fluid, compressible fluid, compressible flow. Is that clear, all of you? Tell me, guys. Now, let me prove that how incompressible flow can be both compressible fluid and incompressible fluid, right? Just check it out. It will take not much time. D rho by dt plus rho delta dot V has to be 0. Now, understand what we are understanding from here. If I just simplify this equation, u into dou rho by dou x plus v into dou rho by dou y plus omega into dou rho by dou z plus rho into dou u by dou x plus dou u by dou y plus dou omega by dou z plus t rho by dt. That is a full-fledged complete equation we have, right? Now, here I will be taking two cases. Now, understand, when density is constant, which case incompressible fluid, incompressible fluid, for example. Now, in this case, my dear friend, understand, in this case, density will be constant means what? Dou rho by dou x. Whether you understood this equation or not, full-fledged equation, 3D continued equation. Tell me, guys, all of you, whether you understood or not. You know this equation, right? From our first slide, what we have started this continued equations or mass conservation equations, that you know comfortably, that you know, right? Now, understand what I'm saying. Understand what I'm saying. If density will be constant, dou rho by dou x will be 0, dou rho by dou y will be 0, dou rho by dou z will be 0, dou rho by dou t will be 0. So this term will be gone, this term will be gone, this term will be gone, this term will be gone. You will left with only these equations. And what is this? Volumetric strain rate will be 0. So incompressible flow will lead to incompressible flow. Incompressible fluid will lead to incompressible flow. That is what the condition of incompressible flow. Volumetric strain rate has to be 0. Now, second possibility, compressible fluid. For example, I am taking compressible fluid. Compressible fluid means density is not constant. It may vary with respect to x, with respect to y, with respect to z, with respect to t. Now, for example, dou rho by dou x is not equal to 0. Dou rho by dou y is not equal to 0. Dou rho by dou z is also not equal to 0. Dou rho by dou t is also not equal to 0. Now you have to struggle, guys. See, even though question is not that much high quality from this zone in your paper, but there is no guarantee that next year they will not ask a very quality question from this particular topic. And if that is will be coming, that will be coming of 2 marks, right? So don't think that, sir, I will simply leave that question. Again, I'm telling you how many subject, how many question you will leave in the examination hall, right? These things are very simple. Sit down after the class and try to revise. These are literally very easy thing. Maybe looking very hard, but it is very easy one. Now, here understand, suppose I'm taking same equation. In this same equation, if these things are not equal to 0, but maybe possibility that compressible fluid can be incompressible flow also when under what certain conditions, when suppose dou rho by dou x, let's say plus 5, dou rho by dou y, let's say minus 5, dou rho by dou z, let's say plus 2, and dou rho by dou t, let's say minus 2, for example. Right. So what you will be understanding, that this term is what, minus 5, complete term. Let me write complete. This term is suppose plus 5. This term is what, minus 5. And this term is what, minus 2. This term is plus 2. So plus 5 minus 5 cancel out. Plus 2 minus 2 cancel out. Again you will left with this equation. So once again you have volumetric strain rate to be 0. So what you are arriving to the conclusions, that whenever you have incompressible flow, it can have both the possibility. It can be compressible fluid, it can be incompressible fluid. In examinations, they just want to avoid one condition, that what we have discussed just now. They have just taken, it is very impossible, very impossible in reality or in practical, that they will be getting plus 5 minus 5 plus 2 minus 2. Mathematically it seems to be possible, practically not at all possible, right? So that's why they assume that incompressible flow will always be incompressible fluid. But once again, this statement is not 100% correct. I have shown you this one condition where compressible fluid can also be incompressible flow, under this very rarest possibility of cases, right? Right. No, where we have unstudy, I'm not discussing anything about the study term, right? We are discussing for our unstudy only, means complete picture we are discussing. Unstudy plus a full detailing we are discussing. We are not taking any special case regarding time, right? Because it is not a function of it is not the constant. That means it can be the function of x, it can be the function of y, it can be the function of z, it can be the function of time. Is that clear, all of you? So this rarest possibility they have neglected in gate examination, because if you see the option, you will confuse like anything. Sir, incompressible flow means what? Okay, study means we can validate this equation. But second statement, incompressible flow. Sir, incompressible flow means two cases: compressible fluid, incompressible fluid. Then, sir, what we have to think? If you are thinking those two things, that it can be compressible also, it can be incompressible fluid also. So definitely, sir, may be possibility that we will not be able to get this particular equation, right? But in gate examination, they forcefully want from us that we have to assume incompressible flow of incompressible fluid. Is that clear? So that density will be constant. If density will be constant, I told you, incompressible fluid, when you take the case of incompressible fluid, where is that? Here. When you take the case of incompressible flow of incompressible fluid, what you will be getting? You will be getting this equation. You will be getting this particular equation, right? And even though you are taking unsteady incompressible flow, once again you will be land up getting the same equations. See, because this thing will be zero, so once again this one. So with the help of only incompressible fluid, we can never decide, or with the help of only incompressible flow, we can never decide whether flow is steady or unsteady. That is the drawback of this discussions. Is that clear, all of you now? Two things are there. Incompressible flow will never guarantee you steadiness or unsteadiness. Second thing, because dou rho by dou t automatically getting zero, density is being constant. Second statement, the steady flow will never guarantee you that the flow is incompressible. Variable density flow can also be possible. Is that clear? Means steady flow will never ensures that density remains constant. No, right? But with the compressible, can we decide steady? How can you decide with the compressible? That is the most difficult case. Compressible means density will not, d rho by dt is not at all zero. Complete derivative of rho with respect to time is not at all zero. Then how can you think of telling whether it is a steady or unsteady? Compressible fluid flow may be possibility that it will be unsteady flow. See, compressible flow means compressible flow. Volumetric strain rate not equal to zero. Volumetric strain rate will not be equal to zero. That means what? What we will be getting? D rho by dt is not equal to zero. Then how can you decide whether rho is a function of, become a function of x, y, z, and t? Because then only it is not equal to zero. So maybe possible that rho is equal to what? Rho naught into e to the power minus t. Then also this d rho by dt will not be equal to zero. Or it may be possible that rho is a function of, rho is nothing but rho naught into x square plus y square. Then in that case, dou rho by dou t may be zero, but dou rho by dou x is not equal to zero. Dou rho by dou y not equal to zero. So very difficult to decide here also. Getting my point? Now tell me this particular problem very quickly. This particular problem. Now, velocity component u and v in a flow field two-dimensional plane motion they have given. They are asking whether fluid is incompressible or not. What we have to do? How to solve that? Whether flow field is incompressible or not. 3D incompressible continuity equation. What is that? 3D incompressible continuity equation. What is that? Dou u by dou x plus dou v by dou y plus dou omega by dou z. If it is equal to zero, directly we have to assume that is nothing but incompressible flow of incompressible fluid. Omega is zero in this term. Dou u by dou u by dou x will be what? 2 minus 2xy Dou v by dou y will be what? 2xy minus 2. This will cancel out. I will be getting equal to 0. And if it is satisfying this equation is what? 3D incompressible flow equation. 3D incompressible flow means what? Fluid is an incompressible flow. That is a correct statement. Whether it is a irrotational or not, let's check it out. Omega xy. What is that? What is that? Dou v by dou x minus dou u by dou y. So here what we can write, or you can calculate omega xy from that also. That is two times. That is half of what is t xy. So dou v by dou x. What is that? Dou v by dou x is what? Dou v by dou x is nothing but y square minus x square, and dou u by dou y will be y square minus x square. So here we can write y square minus x square minus y square plus x square, that is equal to 0. Flow is irrotational. A option is correct. So in the next particular class, we will discuss this flow field is, for this particular flow field, we will define one function, that is a velocity potential function, VPF. How and why we will discuss. Please make a note of it. Once it is done, we can do for the day. So a little bit difficulty might be there in today's class, but try to revise it. The mathematical stuff. No. Okay, guys. Thank you. All of you have noted down? Done, all of you? Yes.